electric current is the rate of flow of charge. We know that charge is the property of matter that allows it to experience a force in an electric field. We know that charge has the symbol Q, and it is measured in coulombs. And we know that whenever we speak about the rate of something, what we are saying is how much of that per unit time. So from this definition, we get the formula for electric current, which tells us that current is the amount of charge that flows past a point in a circuit per unit of time. We know that current has the symbol I, and we know that it is measured in amperes, and we abbreviate that with an A. We know that in order for a current to flow in a circuit, we're obviously here talking about current, meaning moving charge. There are two things that are required. The first is a power source. There needs to be something that is pushing or encouraging the charge to move through the conductors. The second thing is that a closed circuit is required. So two things required for current to flow, that being a power source and a closed circuit. We know that charge would normally follow a fixed path around that closed circuit, and as soon as that circuit is interrupted or opened, we know that we often would use a switch for that. Since the circuit is not closed, current would not be able to flow anymore. Largely speaking, there are two types of electric current, those being alternating current, that being current that changes direction as it moves through the circuit. This is the type of current that we use or have in our households. And there is also direct current, meaning current follows a fixed path around the circuit constantly. This is the kind of current that you would normally get from a battery, because a battery is always responsible for pushing electrons out one end and attracting them towards the other. So in the electric circuits that we deal with, we are going to be dealing with direct current. And then we will often talk about conventional current, which is the original idea of what current was that it is the flow of positive charge, and we know that positive charge would always move from the positive terminal of the battery around the circuit as it is attracted towards the negative terminal of the battery. So conventional current is the flow of positive charge from positive to negative. We know that in reality, though, it is not positive charge that moves in a circuit. It is electrons that move through the circuit. We call that electron current, and it is the flow of electrons or negative charge, which would obviously flow from the negative terminal of the battery around the circuit towards the positive terminal of the battery, and that is called electron current. It's important to note here that the type of current, be it conventional or electron current, does not determine the operation of the circuit. The same rules still apply for current and voltage and resistance in that circuit. It is just the order in which it's followed that changes. A common question for a circuit like this, assuming it's closed, would be one that says that it is measured that 5 coulombs of charge passes a specific point in a circuit every 2 seconds, and you can be asked to calculate the current. We know that current is the rate of flow of charge. There are 5 coulombs passing a point in 2 seconds, which means that the current in that circuit is 2.5 amperes, basically saying 2.5 coulombs of charge pass a point every second. Potential difference is the work done or energy transferred per unit charge to move a positive charge from one point to another. And that definition gives rise to the first formula for potential difference with the symbol V. We know that potential difference is the work done per unit charge, so that is the amount of work done per unit charge, and that is in moving from one point to another. We can also see that since work is measured in joules and charge is measured in coulombs, that the units here would be joules per coulomb, which we also call volts. or abbreviate V. Note here that work done and energy transferred are interchangeable in this case, so the formula can either be W over Q or also E over Q, but both of them still give rise to joules per coulomb, which is then measured in volts. The second part of this definition, which is also important, is per unit charge to move a charge from one point to another. Now this specifies that it's the work done per coulomb of charge between 2 points. So what that tells us is, firstly, it tells us why it is necessary for a voltmeter always to be connected in parallel over a circuit, because what that voltmeter is doing is it is measuring the amount of energy that is used between one point in the circuit and another point in the circuit. The voltmeter is essentially counting the number of coulombs of charge that pass through there and measuring the amount of energy that each coulomb of charge is using to get through that, because we know that resistors slow down current in a circuit, thereby using up energy to pass through that resistor. It is also important to notice the difference between potential difference and electromotive force, or EMF or EMF, which is the energy per unit charge imparted by an energy source. And that is an energy source only, so the EMF that is measured across a battery would also be its potential difference, but EMF refers specifically to energy provided by energy sources, where potential difference refers to the amount of energy that is used per coulomb of charge to move a charge through any part of a circuit. A typical question on potential difference would be something along the lines of saying that this resistor over here is found to use 12 joules of energy for every 3 coulombs of charge. So every 3 coulombs of charge that moves through there uses up 12 joules of energy. What is the potential difference across that resistor? And we can say that V is equal to the amount of work that is done divided by the charge, and that is 12 joules divided by 3 coulombs. And we can say that there are 4 joules per coulomb of charge, or 4 volts of potential difference between these 2 points in the circuit. Resistance is opposition to the flow of electric current. And we know that in order to create a flow of electric current, we need a power source, which in most of our circuits will be a battery, which is a source of direct current. And we also need a closed circuit to allow charge to flow all the way around. That closed circuit is usually created with conductors. We normally use copper wire as our conductor, but essentially they are conductors because they have many free charges. Often they are electrons that allow for electrical energy to be transferred through that material very easily. Now, once we have an electric current, we can actually use that electrical energy to convert into other useful forms of energy, and we do that with resistors. Now, resistors are substances that are made up of different materials that do not necessarily allow charge to flow through them as easily or as freely. Now, we know that the atoms and molecules in those materials are normally arranged in some kind of pattern, and the resistance of a material is determined by how easily charge carriers, again usually electrons but not always, how easily charge carriers can move through that material. So there are a number of factors that affect the ease with which they can move through, or the amount of opposition. The first one is length. We understand that if a resistor is longer, it makes the path that a charge carrier needs to move through it longer, and therefore more difficult, therefore more opposition, and therefore more resistance. The second factor is the thickness of a conductor. We know that if the charges have to move across a very thin conductor, there is a lot of space, therefore a lot of congestion. Think traffic on a road that only has one lane. So the thickness of the conductor, we say that thinner conductors offer more resistance, where as it gets thicker, there is more space for charge to move and therefore less resistance. The fourth factor is temperature. We know that as a substance heats up, we know that the atoms and molecules that it is comprised of vibrate more and more. As those molecules vibrate more, obviously it makes it more and more difficult for charge carriers to move through, which increases the amount of resistance. So we say that the higher the temperature is, the more resistance there is. And finally, the last factor is the type of material. We know that different materials offer different resistances because they have different arrangements of atoms and molecules, which affects the amount of resistance that it offers. So essentially what we have happening in a circuit is we have a battery that starts out by converting chemical energy into electrical energy. That electrical energy is in the form of charges that are moving around the circuit in a current, and those charges then come into contact with the resistors, where different resistors have different functions. We know that some resistors, the friction just causes heat, add resistors heat up. We know that other resistors, as the substance heats up, it starts to glow and give off light. We know that other resistors vibrate and can therefore give off sound energy, and different resistors that make up motors use magnetic energy to convert it into mechanical energy. So essentially, the flow of current around a circuit is all for the purpose of using it on different types of resistors to convert it into different types of energy. We know that heaters use the electrical energy to create friction, which causes heat. We know that lights use electrical energy to heat up a substance so much that it starts to glow, and we know that motors use electrical energy to convert it into mechanical energy, or the energy of motion. And there are four factors that affect the amount of resistance that a substance or material offers, that being length, the longer the substance, the more resistance; thickness, the thinner the substance, the more resistance; type of material determines how easily charge can flow through it; and temperature, we know that the higher the temperature, the more resistance that material offers. Finally, we know that resistance is measured in ohms with the symbol omega, and essentially the resistance tells us how much energy is being used up in order to pass through that specific resistor. Ohm's law states that the current in a conductor is directly proportional to the potential difference across its ends and inversely proportional to the resistance, provided that temperature remains constant. So what this basically tells us is, if we break it down, we can see that current is directly proportional to voltage. The current in a conductor, we know that we have a circuit in which we have flowing current because there's a power source and a closed circuit, and what they are telling us is that the bigger the voltage is between 2 points, the more energy there is, therefore the bigger the current is. So that's the first part of our definition. The second part says the current is inversely proportional to the resistance, which also makes sense to us because we know that resistance is opposition to the flow of charge. So as soon as there is more opposition, the current is going to decrease. And from that, we get our Ohm's law equation that says that I is equal to V over R. What that allows us then to do is it allows us to, if we know the voltage over a conductor and we know the resistance of that conductor or of that resistor, we can calculate the current passing through it. So if this voltmeter here measures 12 volts and we know that this is a 6 ohm light bulb, then we can say the current passing through that light bulb must be 12 over 6, must be 2 amps. Obviously, this only applies when temperature remains constant, because we know that temperature is one of the factors that affects the resistance in a circuit. So if the temperature did not remain constant, we know that the resistance would not remain constant and this formula would not apply. But we are always dealing with ohmic conductors, and we know that ohmic conductors are ones for which this formula I is equal to V over R is always true, basically saying that if we were to draw a graph of voltage versus resistance, our current would always be, while graph would always be a straight line, we know the gradient of that graph is voltage over the resistance, and that is then constant for an ohmic conductor. A non-ohmic conductor would mean as it heats up, the resistance also changes. This formula now obviously has three variables, and so it allows us to rearrange the formula to solve for various unknowns. If we know voltage and resistance through a conductor, then we can calculate the current. If we know the current passing through a conductor and that conductor's resistance, we can then calculate the voltage over that conductor. And if we know the voltage over a conductor and we know the current passing through it, we can calculate the resistance through that conductor. Very important to remember that Ohm's law applies for a specific conductor. So when we are speaking about this conductor, we are talking about the current that is passing through that conductor only, the resistance of that conductor, and the voltage measured over that conductor. It is not the entire circuit's voltage. Ohm's law tells us that the current that passes through a resistor or a conductor is directly proportional to the voltage across the ends of that conductor and inversely proportional to the resistance of that conductor. That is obviously provided that the temperature of the conductor remains constant, because that means that that resistance would remain constant. So we can now use this Ohm's law formula to perform calculations or to calculate unknown variables within a circuit. So here we have a circuit where we can very clearly see that the potential difference across the ends of this resistor is given to us as 3 volts, and the resistance between those 2 points of the potential difference is 2 ohms, which then tells us that the current that is passing through between those 2 points must be exactly 1.5 amps. We can also rearrange this formula to find other unknowns. So here we've been told that there is a current of 4 amps that is passing through this 3 ohm resistor. We know that this ammeter must be connected in series because ammeters must be able to count the amount of charge that passes a point per unit time. So what we know here is we have been told what the current is that is passing through the resistor, as well as what the resistance of that resistor is. So we use Ohm's law once again. We substitute in our 4 amps for the current that we were given, the voltage is our unknown, and the resistance we were told was 3 ohms. We can rearrange this as V is equal to 4 times 3, and we can then therefore say the voltage over this 3 ohm resistor is 12 volts, and you can, if you want to, you can draw a voltmeter in there to illustrate that as your calculation, 12 volts, because voltmeters and ammeters have no impact on the operation of the circuit. Finally, we can use Ohm's law once again to find an unknown resistance, because once again we know that Ohm's law applies here. We know that the voltage across this resistor is 10 volts. We have also been told that the current passing through this resistor is 1.5 amps. The resistance is now our unknown value, and therefore we can say that our resistance is equal to 6.67 ohms. Very important to note here that we always start with the formula as it is given in Ohm's law, as it is given in the formula sheet. Thereafter, you substitute in the values that you have, then you would rearrange and write down the answer. You cannot start out by rearranging your formula immediately as V is equal to I times R. You always start with the formula as given, substitute in the values, and then write down your answer. A series connection is one in which all components are connected along a single path. So in this example over here, we have a battery. Please note the difference here. We know that this is the symbol for a cell, and a battery is more than one cell. So if you have a circuit in which that is drawn, that is a cell, and then multiple cells make a battery. So in this circuit here, we have a battery that is producing an electric current by pushing charge out, and because this is a series connection, we can see that that charge and current is forced to follow a fixed path. It is forced to first pass through ammeter A1. We know that ammeters must always be connected in series so that they can measure the current. It then follows the path along through resistor 1, which is the 3 ohm resistor, followed by the 5 ohm resistor, followed by the 1 ohm resistor, followed by ammeter A2, followed by the light bulb, and then ammeter A3 back into the battery. That is the fixed path that it follows, and there are no variations allowed. The current may not follow another path. We know that the current would never try to flow through a voltmeter, because voltmeters are always connected in parallel, because they have a very high resistance which stops the current flowing through there. So we have here a series connection because everything is in a single path, which creates a series circuit that forces the current to follow the single path. There are 3 rules for series circuits. The first is that current is constant in a series circuit. The reason for this is because the current can only follow a single path. There are no options for the current to increase or decrease as it goes a different route. So what we say here is that the current in one place in a circuit, say for example at ammeter A1, will be exactly the same as the current in every other part of that circuit, because there is only a fixed path. And the way that we write that would be to say that the current through ammeter A1 is equal to the current through ammeter A2, which is equal to the current through ammeter A3, and that would continue for any ammeter that you place in the circuit. The second rule is that voltage is divided. We know that the battery is providing the electromotive force for the charge to flow around the circuit. We know that essentially the battery is providing energy, and that energy must be used up at the resistors in the circuit. So we know that we have 4 resistors, 1, 2, 3, 4, and the energy will be divided amongst those resistors, not necessarily equally. It depends on the amount of resistance, but we say that the voltage is divided, which essentially tells us that the total voltage provided, in this case our EMF, is equal to the voltage used at each resistor, those being V1, V2, V3, and V4. So we say that voltage is always divided in a series circuit. And finally, the total resistance in a circuit is added. Because we're saying that the current must pass through every single resistor, that means that the total resistance in a circuit would be equal to the sum of each resistor in that circuit, R1 plus R2 plus R3 plus R4 in this case. It is important to note here that each voltmeter is measuring the voltage across an individual resistor, so it measures the current passing through there, through that resistance. It is also possible to draw a voltmeter that spans 2 resistors, in which case we know that this voltmeter would be the sum of those 2, because it is equal to the amount of energy that's used between those 2 points plus the amount of energy used between those 2 points. So with these rules for series connections, current is always constant, voltage is divided, and resistance is added. You can now use Ohm's law to solve for any unknowns in any series connection that you are given. A parallel connection is one in which some components are connected along multiple paths. So what that tells us is that we know a series connection is one in which the current is required to follow a single path. So this current passing out of this battery here, note that this battery is now made up of 3 cells, and so the current would follow the direct path where it must go through ammeter A1, it must go through the 2 ohm resistor, it will not pass through a voltmeter because the resistance is high. The current then passes through ammeter A3, it will not go through voltmeter V2, and then we reach a parallel connection. The reason for this is that until now the current has not had a choice about the path it follows. But at this point, the current now has a choice to either follow this path, which leads it through the 3 ohm resistor and then ammeter A3, or it can follow this path, which leads it through the 2 ohm resistor, then the 2 ohm resistor, then ammeter A4, and then the current would rejoin again, where we say that that current then follows a fixed path through the 3 ohm resistor and back to the battery. So note here that we are speaking specifically about the parallel connection where the path splits. So there are some elements of this circuit that are in series, but we would still call this a parallel circuit because it contains a parallel connection. Now, as with series circuits, there are 3 rules that apply in parallel connections. The first one is that the current is divided. As we can see here, since the current splits, it cannot go in equal amounts on 2 different paths. So what we say is that the current must be divided between those 2 paths. So what we can see is that the total current, A2, the current passing through ammeter A2 before it splits, must be equal to the current, the sum of the currents on all of the paths in this parallel circuit. So in this case, that is equal to the current that is passing through ammeter A3 plus the current that is passing through ammeter A4. So the first rule for parallel circuits is that the current is divided. Obviously, if there were more arms or more paths for the current to follow, then that would be split between more different routes. The next one is that voltage is constant. The reason for this is because of the relationship between current and voltage. We know that the current is going to try to follow the path of least resistance. So in this case, there's a path that has 3 ohms of resistance, so more current will go along the path with less resistance, which means the current will be higher, which means the voltage will be higher. Whereas on this path, the current will be lower, but the resistance is higher. Both of these result in the voltages being exactly the same. So we say that the voltage that is measured, or the potential difference measured across the entire parallel circuit, in this case that is V2, must be equal to the potential difference measured across any arm of the parallel circuit. Note that this voltmeter must be connected across both resistors because that is the entire arm. So we say that the voltage across any arm of a parallel connection must be the same as the voltage across the total parallel connection. So we say the second rule is that voltage is constant. The third rule is that, as we can see here, because the current is able to split, it has an effect of reducing the amount of resistance in the circuit. And the way that we show that is we show that 1 over the parallel resistance, meaning the equivalent resistance between this point and this point, is equal to 1 over the resistance of one arm, that being this side over here, plus, we're going to call this resistor 1, we're going to call that resistor 2 and 3, and we're going to say that 1 over the total parallel resistance is equal to 1 over the total resistance in one arm, plus 1 over the total resistance, which in this case is the sum of those 2 resistors, in the other arm. The result here is that the parallel resistance, the equivalent resistance between those 2 points, will always be less than the smallest resistor in any arm of the parallel circuit. The reason for that is because the current splits, there are fewer paths, or there are more paths to follow, therefore the resistance is reduced in that circuit. So once again, a parallel connection in a circuit will always divide the current because current must choose a path to follow. The voltage across any arm of that parallel circuit will always be constant and equal to the total voltage across the entire parallel connection, and the resistance will always be reduced because there are now more paths to follow, and therefore the equivalent resistance will be lower than the individual resistance of any arm. Once you have an understanding for these 3 rules, you can once again use Ohm's law to solve for any unknowns in a parallel connection or a parallel circuit. Power is the rate at which work is done. And so specifically electrical power, when we are talking about the work that is being done here, we know that is a conversion from electrical energy into some other form of useful energy. Our most common examples that we will be using are light bulbs, where we convert it from electrical energy into light energy, or resistors, where we convert it into heat energy. But essentially the work that they are referring to here is whatever the resistor is doing, that conversion of energy from one form to another. We know that from the definition, power being the rate at which work is done, we know that whenever there is a rate, it is always just that substance over time. So in this case, it is work per unit time. And we also know that this can be rewritten as power being work over time can also be where we know that work over charge and charge over time are two separate terms that we already know: voltage, or potential difference, and current. So we can say that power is the product of the voltage across a specific resistor and the current that is passing through that resistor. Obviously, using Ohm's law, we can rewrite this where we know that current is equal to voltage divided by resistance. So we can then get voltage where current is voltage over resistance. So we can then find another formula for power as V squared over R. We can also, since we know that voltage is current times resistance, we can also find the following formula: power is equal to I squared times R. Again, all of these refer to the resistance of a specific resistor that we are determining the power for, the current that is passing through that resistor, and the voltage across the ends of that resistor. So we have three, or essentially four, formulae that we can use to determine the power consumption of a device. We know that power is measured in joules. So when we say that the power of a light bulb is 10 watts, what we're actually saying is that that light bulb is consuming or using or converting 10 joules of energy per second into another form of energy. In an introduction to electricity, it is safe to assume that batteries only provide energy and do not use any energy themselves. And so we can say that the potential difference of a battery or over a battery is equal to the amount of energy that that battery provides per coulomb of charge. So a 12-volt battery, we would have said, provides 12 joules of energy per coulomb of charge. Now, in reality, we find that batteries require a certain amount of energy to pass the charge through them. And so there's going to be a certain amount of energy lost to something that we call internal resistance within that battery. And so in an electric circuit, we illustrate that internal resistance by drawing a small resistor and often drawing a dotted line that shows that that is all considered to be one item. So we say the resistance is included or inside that battery, and internal resistance is denoted with a lowercase letter r. Now, because that internal resistance is within the battery, any energy that is used inside that battery is considered to be lost because it is not able to be used in the external circuit, which is why we have a battery. And so we call the potential difference, or the voltage that is lost to internal resistance, the lost volts. And it is obviously equal to the current that is passing through the battery and through the entire system multiplied by the internal resistance of that battery. So what we find now is we actually have almost two circuits, where one of them is the internal circuit, the circuit that is inside the battery. As the current passes through, it interacts with the resistance within the battery and therefore loses energy. And then we also have an external circuit. The external circuit is essentially what you would use that battery for, whether it's a light bulb or a heater or any other type of resistor. And we call that the load. Obviously, we use a battery because we want it to do a job, and we call the potential difference that is used in the external circuit V load, and that is going to be equal to the current that is passing around in that circuit multiplied by the external resistance, R external. What this now tells us is that the total amount of energy that a battery provides is no longer only going to the external circuit, but it is now the sum of the two circuits, the internal and the external circuit. And we call that total amount of energy per unit charge imparted by an energy source the EMF, also known as the electromotive force. And we say that the EMF of a battery is equal to the load voltage, the amount of energy able to be used in the external circuit, plus the lost volts, the amount of energy that is lost inside the battery. And so what we can do is we can then simplify that to say that our load voltage is I times R external, the lost volts is I times R internal, which means we can simplify this to find the equation for circuits that contain an internal resistance as E is equal to I R external plus R internal. Now this can often cause confusion because now there are three voltages or potential differences that can be obtained from the battery. And so I'm going to just illustrate exactly which is which. We know that the EMF is the total amount of energy that a battery can provide, and so that would often be what is called the marked voltage. So when you buy a 12-volt battery, they are telling you that is the total amount of energy that that battery is capable of providing. The second one is that we'll find here in an open circuit. So when the switch is open, we know in an open circuit, because it is open, there is no current flowing, which means our current is equal to 0. And if there is no current flowing, then what that means is that our number of lost volts must be equal to 0, because lost volts is current times resistance. So what that tells us is that the voltage measured over the battery in an open circuit is our EMF. Because there are no lost volts, our EMF in that case is equal to the open circuit voltage, the voltage measured over a battery when the circuit is open. What we then find is that when we close the circuit or complete the circuit, we will find that a current starts to flow. As the current starts to flow, we know that there are going to be a certain number of lost volts, and then the voltage measured over the battery is no longer your EMF, it is then your V load. And what we can then also see is that the difference between our EMF and our V load is going to be our number of lost volts. It's the difference between EMF and V load, which can be obtained by rearranging this equation over here. Finally, it's important to remember now when using Ohm's law that you either, if you are using R total, then your total resistance you need to specify whether that includes only the external resistance or external plus internal, because if it includes both of these, in order to successfully use Ohm's law, you must then use the total amount of energy provided by that circuit. So you would either say that your total current in a circuit is equal to the total amount of energy provided in the circuit over the total amount of resistance in the circuit, or you could say that the current is equal to the total amount of energy used in the external circuit divided by the total amount of resistance in the external circuit, or you could say it is the total amount of energy used in the internal circuit divided by the resistance in the internal circuit. All of these now apply, but do not make the mistake of using the EMF of the battery with only the external resistance, or vice versa. Once we understand the three rules behind a series connection, we can then use Ohm's law to calculate unknown values within that circuit. So in this example over here, if we want to find the current in the circuit, we would start by, since we know already what the total voltage provided is by that battery, we would now start by calculating what the total resistance is. We know that in a series circuit, the resistance is added, which means that the total resistance here is the sum of the 3 ohm, the 5 ohm, the 1 ohm, and the 3 ohm resistors, which means that the total resistance in this circuit must then be 12 ohms. Once we know what our total resistance is, and we know what our total voltage is, we can use Ohm's law to say that our current must be equal to the total voltage divided by the total resistance. In this case, we've been given a total voltage of 20 volts for that battery. Total resistance we've calculated as 12, and we can then see here that our current in this circuit must be 1.67 amps. And because we know our rules for series connections, we know that the current at this point is 1.67, and this point is 1.67, and this point, and this point. The current is constant everywhere in that circuit. The next thing that we can calculate is we can calculate the voltage over individual resistors. So this voltmeter V1, we can say, since we know what the current is that's passing through it and we know the resistance, we can use Ohm's law once again to calculate that voltage. We can say that the current, being constant in series, is 1.67. Voltages are unknown. The resistance we've told is 3 ohms. Note here that you always take the resistance that is between the 2 points on that voltmeter, which means then that our reading on voltmeter V1 would be 5.01 volts. We can do this again. The same thing would apply for this here. We can see that the current is the same, the resistance is the same, and therefore the voltmeter reading on V4 would also be 5.01 volts. What we can then see, if we call this voltmeter V5 here, is it is possible to calculate the voltage over multiple resistors because we know that the current through those resistors remains constant. We know that the resistance there is added, so we can once again use Ohm's law to say that the voltage over those 2 resistors is equal to the sum of those 2 resistors and the current, which remains constant, as 1.67. Our voltage is the unknown and the resistance is the sum of 5 and 1, and we can then safely say that the voltage across those 2 resistors is then 10.02 volts. What we can now also do is we can see that the second rule for series connections also applies, because we can now see that our total voltage provided is 20 volts and the total voltage used is the sum of V1, which we worked out as 5.01 volts, V2 and 3, which we can combine to call V5 as 10.02, and R4 or V4 as 5.01, and we see that gets us to a value of 20.04 volts. Obviously this 0.04 here is just because we have rounded our current off and is negligible and would not penalize you at all. So what we are trying to get at here is we're trying to show that using your 3 laws for series connections and Ohm's law, you can always solve for unknown values in your circuit. Once we understand that current is always divided, voltage is always constant, and resistance is reduced in a parallel connection, we can once again use Ohm's law to perform calculations to find unknowns in these circuits or connections. So the first thing that you would want to do in a parallel connection is you would always want to calculate what the equivalent parallel resistance is, and that is done by taking the sum of each arm's resistance. So in this case that is going to be 1 over the parallel resistance is equal to 1 over 3 plus there's 2 ohms plus 2 ohms in series here, and that then gives us 1 over 3 plus 1 over 4, and which is equal to 7 over 12. It's important to note here that 1 over RP equals 7 over 12, and therefore RP is equal to 12 over 7, which is 1.71 ohms. So what that tells us is that this entire connection here is the equivalent of a single 1.71 ohm resistor connected in series. Now once we've done that, we can calculate the total resistance in the circuit. We know that the total resistance, if you just follow this path, is going to be your 2 ohm resistor plus your equivalent parallel resistance 1.71 plus your 3 ohm resistor. So our total resistance in this circuit is then going to be 6.71 ohms. Once we have an understanding for our total resistance, we know that the battery is providing a total voltage of 30 volts, so we can use Ohm's law to say that the total current in the circuit is equal to the total voltage divided by the total resistance, that being 30 volts divided by our total that we've just calculated of 6.71 ohms, which tells us that the total current in this circuit is then 4.47 amps. It's important to note that that is the total series current. We know that current is divided in a parallel circuit, so it is going to split at that point, but we now know that that is going to be the reading on ammeter A1 and A2 because they are in series. What we now start to look at is what is the voltage measured by V2, and we can once again use Ohm's law. Ohm's law tells us that the current is directly proportional to the voltage across those 2 points and inversely proportional to the resistance. We know that the resistance is just the equivalent parallel resistance. So our current, we've been told we know the current at this point and at this point is going to be 4.47 amps. The voltage is our unknown, and the resistance is that parallel equivalent resistance of 1.71, which we can then solve to find that our voltage for V2 is then 7.64 volts. Since we know our rules for parallel connections, that means that V2 must be equal to V3 because it is equal to the voltage across that path of the circuit, and it is also equal to V4 since that is a separate path on the circuit. What that then allows us to do is, since we know the voltage V3, we know the resistance, we can calculate the current through A3, and we say that the current through A3 is equal to the voltage that is measured across that arm of the circuit, which is exactly our parallel voltage, divided by the resistance, and that then gives us our parallel voltage 7.64 divided by our total resistance of 3 ohms, and that tells us that our current through A3 is 2.55 amps. We can then similarly calculate the current that is passing through A4, saying A4 is equal to, again, the parallel voltage. We know the resistance in that arm, so we can then substitute the same parallel voltage because it is constant in parallel, divided by the total resistance of 4 ohms this time, which gives us a current of 1.91 amps. And then this also reinforces our rule for parallel circuits, because we can see here that the current that is passing through this parallel circuit, the current through A2, is equal to the sum of the current passing through A3 and A4, which shows again that current is divided in a parallel circuit. So as we can see here, the rules, once you understand them, allow you to use Ohm's law to solve for unknowns. Very important to understand that the voltage measured across the entire parallel circuit is equal to the voltage measured across each arm of the parallel circuit, provided that it covers every resistor in that parallel circuit. We know that if we wanted to calculate the voltage over only one of those resistors, that would then be a separate value, because you would have to say that the voltage here is different because it is now being divided in that series circuit. And so we would say the current, which we have calculated at A4 1.91, is equal to the voltage, that's the unknown, over only that 2 ohm resistor, which then tells us that that voltage there would be equal to 3.82 volts. And that should make sense, because if we double that 3.82 volts, we will see that it is exactly that voltage for V4, which shows again that that voltage there must be shared. So these rules are important to understand as they help with the calculations. Once you understand the rules for parallel connection, it's possible to do calculations. So here we've been given a circuit. There's a 12-volt battery, a current of 5 amps being measured in that circuit, and then 3 resistors in parallel with each other, and 1 resistor of unknown resistance with a voltmeter connected over it. So our first problem to solve is always to calculate the equivalent parallel resistance, and we do that by saying that we know that 1 over the parallel equivalent is equal to 1 over each resistor. So 1 over the 3 ohm, 1 over the 2 ohm, 1 over the 1 ohm resistor, which we find comes to a total of 11 over 6. But we want the parallel resistance, so we say the parallel resistance is therefore equal to 6 over 11, or 0.55, simplified or rounded to 2 decimal places. What we can do next is we can calculate the voltage that is being used over this parallel set. So just to make it easier to visualize, we can draw in a voltmeter here that's called VP, the voltage over the parallel set. And we can calculate that by saying that we know that voltage is always equal to the product of the resistance between the 2 points, in that case, or in this case it is RP, multiplied by the current passing through those points, which we've been told is 5 amps, that is the current, and we get 0.55 ohms multiplied by 5 amps. That tells us that the voltage over the parallel circuit or parallel connection is 2.75 volts. Once we've done that, we can calculate the voltage measured over or measured by V1, because we know that the total voltage provided by the battery, being 12 volts, must be equal to the sum of the 2 voltages that are used in this circuit. In this case, that is V1 plus V parallel. Again, we know that the total voltage provided by a battery must be used in that external circuit, and there are only 2 places where it can be used, V1 and VP. So we were told the battery has a voltage of 12 volts, V1 is our unknown, and the parallel voltage we just calculated as 2.75 volts, which allows us to solve to find that V1 must have a voltage of 9.25 volts. Once we have this, we can now calculate what this unknown resistance is here, because we know that resistance is always equal to the voltage that's measured over that resistor divided by the current passing through that resistor. We know that current in a series circuit remains constant. So in this case, that is the voltage V1, which we've just calculated as 9.25, divided by the current, which we were told was 5 amps, which tells us that the resistance of that unknown resistor must be 1.85 ohms. Finally, what we could also be asked here is we could be asked to calculate the current that is passing through each part of this parallel set. So we can start by calculating the current passing through the 1 ohm resistor, and we do that because we know that current is always equal to the voltage divided by the resistance, and we know that voltage in parallel is constant, meaning the voltage over each one of those resistors remains the same. So we can say that the voltage we know is 2.75 divided by that 1 ohm resistor. That means the current passing through the 1 ohm resistor is 2.75 amps. We can then also calculate the current passing through the 2 ohm resistor with the same calculation, except now knowing that the voltage remains the same but the resistance changes, so it's now 2.75 divided by 2, which we find is 1.375, which we obviously then round to 1.38 amps. And then finally we can calculate the voltage through the 3 ohm resistor, and same calculation, voltage is current is equal to the parallel voltage, which we know remains constant, divided by that resistance. Again, parallel voltage 2.75, resistance now 3, meaning that the current passing through that resistor is then 0.92 amps. We can check that this is correct by seeing whether these 3 currents add up to make up that total amount of current, and we find that the current that is passing through the 1 ohm resistor plus the current passing through the 2 ohm resistor plus the current passing through the 3 ohm resistor is equal to 2.75 plus 1.38 plus 0.92, and we find that gets us to a total current of 5.05 amps. The reason why there's a slight difference between those two is obviously because we've rounded our answers as we go.